Hello, science enthusiasts. Welcome to Science Chat. It's part of our Spaces Unleashed program here on Twitter. Today, we are simulcasting live to the Wisdom app as well. So we're in two places at once. Every week, we invite an amazing guest to come to us and talk about their area of knowledge. After a little interview, we open up the floor to questions. So if you're on Wisdom, you'll have to wait a sec to come up to ask a question of Dr. Scholtz. And if you're on Twitter Spaces and you've been to one of our shows before, you know the drill. My awesome co-host is Chris Sikowski. She's going to be working behind the scenes to help me out. Without further ado, welcome Dr. Jan Scholtz, black hole specialist. How are you doing today?
I'm great. Thank you very much. Thanks for the great opportunity to talk to you guys. It's always fun.
I know. I'm very excited to talk to you again. Spoiler alert, Dr. Scholtz was a guest on the Science Podcast. And you are a trooper because are you in Sweden still?
No,
not Sweden.
I'm
sorry.
in UK, actually.
Oh, okay.
I remember when we did the interview last time, I was actually booking my movers. Or I was trying to figure out movers. So I am now in Cambridge in UK. I started my new job here in October.
Gotcha. Right. So, but I mean, it's like 1 o'clock in the morning for you, our time right now.
Yes, it is.
So thank you. I would need a little bit of coffee to be as peppy as I am right now. But I hope you'll feed off the energy of the room. We've got tons of folks in here listening, which is awesome. And one of the first questions I have for you, Dr. Scholtz, is can you tell everybody a little bit about your education?
So I'm originally from Prague, but I did my A-levels, which is the last 2 years of high school or college, basically the last year of school in UK. There I was primarily focused on physics, chemistry, and maths. Mm-hmm. I then did basically joined bachelor's plus master's at the University of Cardiff in Wales, mm-hmm. Where I originally started with physics, but then I moved with physics and astronomy, and I essentially had astronomy-based master's dissertation. And then I did my PhD at the University of Durham in astronomy, which was purely It wasn't actually purely observational astronomy because I did sort of a lot of comparison with theoretical simulations. Mostly observational based astronomy.
Now, what would you call yourself, Dr. Scholtz? Like an astronomer?
I think I would call myself an astronomer.
Yeah.
I was actually thinking about it today. However, just the thought of calling myself an astronomer, even though I have an astronomy PhD, it still feels really weird. I got my PhD 2.5 years ago. And it still feels kind of not absurd, but definitely oh my goodness, I am actually an astronomer. 9 years or 8 years of education, and an astronomer.
Okay.
Your Twitter handle says that you're a logic wizard. Can you explain a little bit about that?
So that's a reference to Disenchantment on Netflix.
Oh, on Netflix.
Because they, the main character Bean, at some point, see somebody meet somebody and it's like, oh, I'm a scientist, and she mispronounced it to scientist, and then she's like, but actually I like to call myself a logic wizard. And I just think it's such a funny exchange of the sort of fantasy world meeting the steampunk world in that scene, that I just put it as a joke.
Gotcha.
Yeah.
Great question, Chris. I was thinking about asking the doc that, and I was kind of shy to ask what it was.
I don't mind. I don't mind asking. I was curious. So curiosity.
That's the right attitude.
That is the right attitude for a logic wizard, Chris, is being curious. What got you into science? You got into all of this stuff with your education, a PhD in astronomy. Were you a kid that loved science when you were young?
On some level, yes, even though I never realized it. So my dad is he studied aeronautical engineering. He then completely moved to something different, still with airplanes and helicopters, but very much different.
Mm-hmm.
And my mom, because of political reasons during the communist times, she actually wasn't allowed to study at university, but she basically did two high school degrees in chemistry to get her qualification, and she works in a lab. But so I was always close to science. I always really enjoyed maths, chemistry, physics. My brother eventually he's 7 years older. He got a PhD in particle physics and cosmology.
Wow.
So he's very much there as well. I always make fun that he's actually the smart one from the two of us because he's doing like proper maths, unlike me. But I was always interested, and I think I mostly just followed the science because I was good at it and I didn't know what else to do. And then I started with a degree in physics, not physics and astronomy or not astrophysics that I could do, because I thought, no, I want as much general physics as possible. And then in my first year, I first time discovered of how much science you can do at other wavelengths than optical wavelengths, right? Of like what we can see with our eyes, but you can use infrared, you can use radio, you can study the sort of heat emission of the universe and the galaxies, and it blew my mind. I think this was the first time I was never excited looking at the sky and stargazing. I always considered the night sky kind of boring. I think it's mostly because I grew up in a big city.
You had light pollution.
We had huge light pollution in Prague.
Yeah.
But I never was kind of like inspired by the sky. Like I was just like, no, it just doesn't do to me. But the moment I saw galaxies at like the dust emission from galaxies, and I could see that actually what looks like just a dark cloud in optical light is actually in infrared, is this vibrant thing of just star formation.
Yeah,
I couldn't resist that. I think that was the moment I was like, okay, I need to learn more. I need to know more. So
I love it.
Complete coincidence on some level.
I love it. Yeah, that's so cool. Both Chris and I teach the Alberta curriculum where we're from, and there's a section of it about space, and just everything about space is new to a lot of the students, and just talking about there's different types of light, and they're like, what are you talking about? So even something like that just blows their mind away. Like it's kind of cool. I can see why it was such a hook for you.
I think this is the first thing that we have to explain when we start talking about, like when we do outreach, is look, there's light. What you consider a light, and in terms of optical light, is a very, very narrow part of the entire electromagnetic spectrum. Mm-hmm. And the moment microwave is a type of light, and microwave light is actually incredibly important because that's where we can see the remnants of the Big Bang from 13.7 billion years, for example, right? Yeah. The CMB. X-rays is incredibly important. So, yeah. It's the most exciting part. We call it multi-wavelength when we use multiple colors. So that's always exciting.
I love it. Now let's get into some of the stuff that you know a lot about, and it's going to excite everybody that's listening. Can you talk to us about these supermassive black holes? Like, just saying it sounds really cool. Could you talk a little bit about it?
So so I think most of the people know me as like the supermassive black hole person, but I'm more of a galaxy evolution, and supermassive black hole plays an incredibly important role in it.
Okay.
So I think everybody knows kind of about sort of the core concept of black holes, right? It's something that is so incredibly dense. It's so incredibly massive and compact that not even light can escape it, right? So basically, that's why whatever falls into it, it's never going to you're never going to see it again, right? It's never going to come out again.
So you're saying, however, what happens in a black hole stays in a black hole?
Yes. Yeah, it's actually second time I hear that joke in like a week.
Sorry,
and I
Doc.
was like, how was it that I spent like 6 years of working on this and we never made that joke in any conferences? It's embarrassing for astronomy. Like, come on, we need to do better. Thank you. But so one thing important, black holes are still just sort of governed by the gravity, right? On larger scale, like when you go a little bit further. For example, if sun would suddenly turn into a supermassive black hole, Earth and the planets would still orbit exactly the same as they are right now, because the black hole would still have the same weight or mass as the sun, and therefore all the orbits would still be of the planets would still be exactly the same, right? Because the orbits of the planets really depend on the masses of the planets and masses of the mass of the sun. So they are not magical. So that's important to know. However, they are also just incredible, because once you fall in, you can't get out.
Do these
supermassive black holes?
Sorry. Go ahead, Doc.
Yes, go ahead.
No, go ahead. I'll have a question, I think, after this next part. Go ahead.
Supermassive black holes are these rare things where they are in the center of the galaxies. There's always one in the center of a galaxy. There can be two, potentially, but that's usually when two galaxies are have merged, they've collided and merged, and now their supermassive black holes are going to merge together, or they're going to become one. And these supermassive black holes can have, I think, like around 1% mass of the galaxy. So you can imagine. So, for example, mass of the Milky Way is roughly 1,000 billion masses of the sun. A little bit less, actually. I think maybe 100 billion solar masses. Milky Way, actually, black hole is very much a bad, because that one is quite, Milky Way supermassive black hole is actually quite small of what we would normally expect. It's only 1 million masses of the sun, which I know it sounds ridiculously high, but actually they are objects. There are galaxies that have inside a supermassive black hole of 1 billion solar masses, or masses of the sun, right? As we have set up the unit. And they're just there in the middle. The incredible thing about these is that there is something that sometimes you can feed the supermassive black hole, but you literally feed it gas, right? Like mostly hydrogen, right? Mm-hmm. Most of the gas in galaxies is hydrogen. And as you start falling into the gravitational, sort of what we call gravitational well, you might have heard that term. You have to somehow, this becomes a little bit physicsy, but you don't have to completely understand everything. It's just sort of just the end, and that is you have to convert the potential energy, because you are falling down, right? So you have to convert that energy into something. You convert it to heat, and that will create an accretion disk, which I think some people might have heard. And it's essentially a disk of super hot gas that's around the supermassive black hole, and it's basically sort of packing onto the supermassive black hole, eventually sort of falling in. But it has to radiate enormous amount of energy. And it's over the sort of a growth of a supermassive black hole, you release more energy into the surrounding area, into the surrounding sort of galaxy, than what is the energy that you need in order to keep the galaxy together. So essentially, how people can sometimes look at it is that if you think about Death Star laser and Alderaan, where they would just shoot the laser into Alderaan and it would just blow up apart. Supermassive black holes, and when they are accreting something called, they become active galactic nuclei, because they are active and they are inside a galactic nucleus, right in the center.
In the center, yeah.
Or in the end. But so they can actually rip the galaxy apart. Now, they don't actually release it as a one laser burst, right? They release it over 11, 12 billion years. So we have seen galaxies these days. Therefore, we know that the galaxies survive. But they probably have, or we believe they have, a profound effect on the life of the galaxy and how the galaxies sort of live, and especially die, how they stop forming stars at some point.
They run out of stuff because it goes into the black hole. In a way, or not so much?
Not necessarily. There's actually way more gas around.
Okay.
There are currently two. One is that it removes the gas because it creates these what we call outflows. It's essentially there are these galactic winds that go from the center of the galaxy, from the black hole, out into the sort of out of the galaxy. So we think that it actually removes the gas from the galaxy. That can be one.
Oh, it blows it away.
It blows it away. It blows it away to like out of the galaxy.
Okay.
Right. Or the second one is the gas. In order to form stars, you need the gas to be actually cold, around 20 to 30 Kelvin. So that's minus 250, minus 240 degrees Celsius.
It's a little chilly.
So if you suddenly, I think even for Canadians, that's chilly.
Yeah, it's pretty chilly for us.
Yeah. So even so if you raise the temperature by, I don't know, tens of degrees, you actually make it stop forming stars. So the other theory that it actually doesn't remove the gas completely, it just heats it up and prevents it from forming stars.
Blows it away and makes it a bit too hot.
Yeah, it's one or the other. And literally we are quite literally organizing a conference on it, the two conferences in September, one here in Cambridge and another one in Iceland.
Wow.
Where the sole discussion is going to be, so which one is it, guys? Like, we don't know.
You're going to have a super debate, a super nerdy debate about black hole stuff, hey?
Yeah. It's literally going to be like 5. I think both of them are for 5 days. We are literally talking about. It's like, okay, so what? Okay, guys, like, what is happening?
That's awesome.
And I can guarantee you that we are going to walk away with like, oh, we still don't know. Like, I'm just one side note. I'm currently for those who don't know how these scientific conferences and workshops work. If you want to present your work, you usually have to send like an application because we have limited amount of slots for like these talks, roughly 15 to 20 minutes.
Yeah.
So as one of the person on the organizing committee, my job is to actually read what we call the abstracts, basically the application saying, oh, I have done this work and I would like to present it to you. And literally we have right now where half of the abstracts, half of the applications are saying, oh, it's definitely this one. And then we have other one which is saying, oh, it has been already established, it's the other one. And we are just now confirming it. And we're like, guys, you're both very sure that it's one or the other.
That's interesting that you bring that up because there is debate in science about a lot of things. There's people on the different sides of the fence and there is debate, right? Science doesn't know everything. And I think that's a really important thing that you brought up.
I think I assume that a lot of the questions people are going to ask today, I would be like, I don't know. And I don't think we actually know as a community, as a science community, what is happening.
So I have a lot of follow-up questions about black holes, but I think I'm going to pocket them because I might steal some of the audience's questions about black holes. If you're just joining us, this is Science Chat. We are simulcasting to Twitter Spaces and the Wisdom social audio app. After an interview that'll be done in about 10 minutes here, 10, 15 minutes, I'm going to open up the floor to questions. So if you've requested on Twitter Spaces, you'll just have to hang out for a sec. And then on Wisdom, if you're listening, you can request to speak on Wisdom. And it should work. The audio should work back and forth between these two platforms. So my other big question is, you study galaxy formations and galaxy evolution. Is there something that you find really interesting or unique or something kind of shocking that you would like to tell our listeners about galaxy evolution / formation?
Hey parents, this message is for you. Do you want your kid to listen to an educational podcast made for kids, edited by a kid, hosted by a kid, where we interview kids? Then subscribe to Chase Your Dreams with Brayden Chase. I'm Brayden Chase. In my podcast, we find out what kids' dreams are and help chase them. Whether it's a job, visiting somewhere, a crazy dream, or anything you can think of. I help them figure out what it takes to chase their dreams. It's educational, and I've been told it's pretty funny too. So what are you waiting for? Hit that subscribe button so your kids can chase their dreams today. Brayden Chase is not responsible for your kids' dreams getting bigger and uncontrollable laughter.
I think I have one which I always find mind-boggling. I hope the audience will find it mind-boggling as well. So, universe was born. The Big Bang was 13.7 billion years, roughly 13.7 billion years ago. It took roughly 300,000 years after the Big Bang for the universe to cool sufficiently that protons and electrons merge together to create atoms. Right?
Mm-hmm.
So that is sort of one like it took quite a long time, right? 300,000 years from a point of view in astronomy, it's actually a really long time. A very, very short time. From our perspective, quite a long time. But yeah, first galaxies, and I'm just confirming my number exactly, just so I don't say anything wrong, because I'm always fascinated by it. I think first galaxies have formed barely 210 million years after the Big Bang, which means that there must have been sufficient amount of hydrogen gas that has sort of started collapsing on itself, creating these pockets of dense environment, right?
Mm.
And then stars were formed in less than 210 million years. I think the best estimate we currently have that it might have taken only 150 million years, maybe less. I'm not exactly sure on these things. So that is just sort of incredibly fast, the way the universe started creating galaxies and everything. And then at first, supermassive black holes, or we can already see supermassive black holes with masses of billion solar masses at roughly 700 million years after the Big Bang. So for some supermassive black holes, it took them only 700 million years to grow.
Wow.
To billion times the mass of our sun.
And that is
a huge problem, by the way. Okay. We don't know how they did it.
You don't know. I was going to say, it seems awfully quick.
Yeah, it's awfully quick. So luckily, sort of exponential growth helps you. So the bigger you are, the easier it is to grow even more. Oh. But it sometimes is not just the limitations of how much you can grow on sort of like the tiny sort of scales of right next to the black hole. Sometimes it's about how do you funnel this amount of gas into the center of the galaxy. And I think last Friday, on Friday we had a paper where they were running simulations, and they were like, you need to start with a black hole that's already around 1,000 solar masses so that it has time to grow into a billion solar mass in 650 million years. And creating a black hole that's 1,000 solar masses out of a star, which is normally how we consider how we would normally form a black hole in the first place, is incredibly hard. So there are these questions of like, okay, did we mess up our observations at 700 million years after the Big Bang, we don't actually see a billion solar mass black holes. They are actually smaller. We just overestimated their mass. Or is there, and therefore we don't understand fully some physics, or is it actually sort of easier to do these things, to grow these things, because we don't understand some sort of physics? But there is some physics that we, as of right now, we do not understand. And That's usually when astronomers get frustrated and be like, okay, let's solve this. But also, we are talking about such a young universe that basically even James Webb Space Telescope, the new one that was launched in December, is barely going to hit those, is just about will be able to hit those distances and those ages of like the first supermassive, first stars and first tiny black hole seeds, or supermassive black hole seeds as we call them. So even with the newest space telescope, it's going to be incredibly tough. So all you can do at the moment is just theoretical modeling and simulations.
Now, are you a scientist that gets frustrated by stuff like that? Like, or do you get excited? Or are you kind of like in between?
I really get excited about it.
Yeah.
I think the ones I am really frustrated about potentially is the things that I know that we can never know, or that we have to completely design something completely new. So, for example, when you study galaxies with this very, very active supermassive black holes, by the way, if you have a very, very like what's called luminous or bright supermassive black holes or accreting supermassive black hole, it becomes a quasar. That's what quasars are. They are just accreting supermassive black holes. But the problem with quasars is that they outshine their host galaxies. They are so bright. They are brighter than the galaxies. So if you want to study their host galaxies, you have tough luck, because it basically just completely outshines the entire thing. All you can see is the accretion disk. You can't see the stars. So that can be frustrating. That's when I get frustrated. I know that there is no way of knowing. Like the nature of the objects that I currently study, it's incredibly hard to figure out some things about their host galaxies.
Just because that quasar is so bright, it drowns all of the other data.
Yeah. Wow. You just see, it just looks like a star.
The whole galaxy looks like a star. That's crazy.
The whole galaxy looks like a star.
That's bananas. That is bananas.
I mean, with like maybe in 15, 20 years, we'll be able to, with the big telescopes, we'll be able to do it. But yeah, this is like, okay, there's not even like a way to be clever about this. This is just frustrating.
Figuring Out Family isn't your ordinary podcast. It's a completely new experience that helps you make your family the best it can be by giving you the deep insights to help your family thrive. You'll learn how to help your family have more productive conversations and manage life's disappointments too. You'll feel inspired by the special guests that are experts in their field of family relationships. Get valuable tips for dealing with difficult family members, repair broken relationships, improving your parenting skills, and keeping your children happy and healthy. Check it out now.
Oh my goodness. I am just stunned at what you said. Like the whole galaxy's as bright as a freaking star. And you can't see anything. It just like blinds you. That's wild. I love it. So the nearest galaxy to us is Andromeda, correct?
Yes.
Yeah. No, is that stuff that people study or not so much because it's so close? Like you're after further away things.
So people study Andromeda a lot.
Okay.
I am just not one of them.
Oh, okay.
So I specialize in something with what I would consider high redshift galaxies. For me, if there are any astronomers or people who know about redshift, for me, high redshift is redshift 1, 2, 3. For those who don't know what that is, it means that I look at the galaxies that were that lived around 7 to 11 billion years ago. And that's because throughout the age of the universe, or through the life of the universe, both the amount of stars, the rate at which stars were forming, and the rate at which black holes were growing, basically peaked around 7 billion, 7.5 or 8 billion years ago. It's basically the way that you needed to wait for the gas from the Big Bang to cool down sufficiently and get on the galaxies. Then there was a peak that was roughly 8 billion years ago. And ever since, we are kind of running out of gas a little bit, and we live in this like sort of bit, not dead, but sort of slow going universe where, okay, like a majority of things happen already. And we are now sort of in the, post midlife crisis universe. I think is the best way to describe it.
Post midlife crisis. So the universe has bought its fancy car and like has been worried about losing some hair.
Yeah, essentially, it's kind of there, and there is a question of whether there's going to be. As a chemist, you are going to absolutely hate astronomers for this.
Well, I am a chemist.
As astronomers, everything heavy, all elements heavier than helium is considered a metal. And the reason is...
So like neon?
That's metal.
Oh my goodness. Okay, I do hate this. I do hate this so much. I hate this so much.
The reason is that for us, metal means something else, and that is that the element needs to be created inside a star or during a supernovae.
I gotcha. Okay.
While hydrogen and helium was created in large abundances, even or in large quantities, right? It was already there after the Big Bang.
Right. Primordial stuff.
Yeah, exactly. Primordial. So like there is a method to the madness, but like every single time I talk to like my friends are like, oh yeah, it's a metal. And I'm like, what are you talking about? It's a gas. But anyway, so metals help cool hydrogen, or hydrogen clouds. The way that suddenly you have way more emission lines that you can get off, you can use to efficiently basically dump the heat away, radiate the heat away. So there are these theories that actually, as we are creating more and more metals or like oxygen, carbon, and others, suddenly cooling might become way more efficient in the next few billion years. And once you have more efficient cooling, your star formation might become suddenly way more efficient again, because you won't require a large amount of gas. You can just form stars way more efficiently in the gas that you already have.
Oh, okay.
So there might be like suddenly a second wave of formation of stars, on like a cosmological scale in a couple of billion years. But that's just a prediction. That's just like a future prediction of what the universe might do.
I love it. Well, you know what? You can make predictions like that because you and I are going to be dead by the time it happens. So
definitely.
So just to reset the room, because we've hit kind of the half an hour mark. This is Science Chat with Dr. Jan Scholtz. It says I did have a nice title, Supermassive Black Hole Expert, but you also study galaxy formation. After I got one more question for you, and then we'll open up the floor to questions from the audience. And my question is about interferometry. Did I say that correctly? Interferometry?
Yes, exactly.
Okay, so like from my science background, I have an idea what it is, but it is critical for what you do. Would you mind explaining what it is and why interferometry is so important?
So I think we'll start with why it's so important.
Okay.
And then we will move into what it is. So when we are talking about resolution of telescopes, we don't talk about the number of pixels. We talk about the optical resolution of telescopes, and that's how far away two objects can be before they merge into just one object, right? So how far two stars on the sky, we measure that in an angle as a sort of arc second, which is 1/1600th of a degree, but that's not important. It's just a bit of an Easter egg. And that will depend on the wavelength of your light, and then divided by the size of your telescope, by the diameter of your telescope. So Hubble, for example, has a resolution of 0.15 arc second with its 2.5 meter mirror. The problem becomes that if you suddenly go from, Hubble, which is 1 micron in wavelength, to something like, I don't know, dust emission, right? Emission like infrared, like the sort of heat emission of dust. you suddenly want to observe something at 1,000 microns. So with a 2.5, so in order to have the same size of your mirror, so same resolution, to do the dust observations, you would have to have a mirror that size of 2,500 meters or 2.5 kilometers.
2.5 kilometers. Okay, yeah, I was going to say that.
Now,
There's no way.
that becomes a little bit tough, right? 2.5 kilometers. You might get a little bit that actually you don't need a perfect mirror, right? Because it's not actually a mirror. It's going to be more of a metal sheet. It's going to be more of a radio antenna at that point. But still, making a 2.5 kilometer radio antenna is impossible right now.
Yeah.
So what you can instead do is you can take, I don't know, like for example, ALMA, which is one of the telescopes I use heavily, is where you take 60 12-meter antennas, you put them around a plateau that are 2.5 kilometers, you link them together, and you make them act like a single telescope with a diameter of 2.5 kilometers. But actually, you only have 60 12-meter telescopes, right? You can feasible. It's incredibly sort of tough. The way you do is that you have to measure not only sort of the energy of the electromagnetic waves that are coming, but you need to also do something like what's something called a phase of how much the light is basically delayed from the object and the individual antennas. Because if you, for example, study a supermassive black hole that's really far away, because it has to travel to a different antenna, so it travels a slightly different length, a slightly different sort of length. It's slightly different far away by maybe 200 meters. But it's enough for us to measure the differences. So we measure those differences, and then that's the technical bit is that we use something called Fourier transforms, which is this amazing mathematical concept. And then slowly you basically sort of create an image of how you would see it if you would have one single big telescope rather than 60 smaller telescopes. People have been doing it in optical wavelength as well. You might know that the very large telescope can be, which is actually 4 telescopes, they can be linked together to create very large telescope interferometry. You can do it at optical. Interferometry is also used heavily in gravitational wave detection. However, there it works a little bit different. They basically have 2 lasers at 90 degrees to each other, and they look at basically the path differences between the 2 arms, between the 2 lasers that the lasers have to travel. So there it's a little bit different, but also sort of the same concept of measuring differences in paths. Gotcha. And yeah, but it has loads of limitations, and because you have so many telescopes, and you have so much data from different telescopes. Your observations the data can be 1.5 terabytes of data. 1.5 terabytes. Single observational. And then you are like, oh, well, okay, I need to do something about it. On the other hand, you can then link telescopes across the entire globe, and you can, which is what the Event Horizon telescopes did. And then you can basically create a telescope the size of the Earth, in more or less. And which meant that they could actually observe an accretion disk or the event horizon of a supermassive black hole in a nearby galaxy, right? In our own galaxy, but also in a nearby, more active galaxy. So you can get so much amazing stuff out of it, but it's a bit of not a nightmare, but it's a lot harder to just looking at an image what we would normally get. Yeah, but that kind of makes sense. Like if you have one person who's looking, and you ask that one single person, and maybe that one single person has a giant eyeball, they're going to be able to tell you what's happening a lot faster than 60 people with slightly smaller eyes who are trying to all agree on what they're seeing. So it might get a little messy, right? The way I imagine you have a telescope with a big mirror, or a big telescope, and then you put a big paper sheet over your lens, and you poke a pinholes or a small holes, and suddenly you can only see actually from the light from the little holes, and you have to sort of merge it all together and figure it out what from. But yeah, but at the same time, we actually get a better image. That's the amazing thing. Right, is that eventually once we combine all the data, we get incredible image out of it.
I love it. Very cool. Okay, thank you. That interferometry is I'm so glad we had a quick chat about it, because it is confusing to think about it, but it's a huge part of what you do and what other astronomers do to study the universe. So it's something that would be completely baffling if somebody came across that term and didn't really understand it. So if you're joining us, we have Dr. Jan Scholtz, our science expert tonight, who's talking with us about black holes and galaxy formations and evolution. And we're going to open up the floor to questions on both Twitter Spaces and Wisdom. So if you do have a question for Dr. Scholtz about what we're talking about tonight, you can request to speak. And Chris will be in charge of Twitter Spaces. And if anybody on Wisdom wants to pop up and ask a question, we can do that. And I think we'll go from there. I think, who is it? SCL has been waiting the longest. Just a reminder, keep your questions on point. If you have a locked account or we're not sure who you are, you may not get up to the stage. So we want to make sure that this is a fun space and an educational space. So I think Chris is bringing people up. We'll go to at STLXO. Do you have a question for Dr. Scholtz?
Can you hear me?
Yep, I can. Hello.
Okay. She said something about light not being able to leave black holes. So I was wondering about gamma rays and new planets forming.
Hey everyone, my name is Catalina. I'm a 2-time cancer survivor and a babe with a mobility aid.
My name is Haley. I'm a PA with POTS and a water allergy. We are the hosts of the Doing It Disabled podcast.
Haley and I are on a mission to create an honest dialogue about living with disability and chronic illness. We would like to open up our corner of the internet to both learn and teach about the lived experiences of the disabled community.
Join us as we navigate this world that was not created with us in mind and watch how we do it disabled. Head on over to Spotify and check us out.
So questions about do gamma rays come out of a black hole or just gamma rays in general?
Do they come out of black holes?
Oh, okay. All right. Do gamma rays come out of a black hole, Dr. Scholtz?
Yes. Gamma rays are, so I think this might be a connection to gamma ray bursts. So gamma rays, for those who don't know, they are just these massively energetic either particles or photons. Imagine sort of an electron or even something lighter than an electron with the energy of a baseball flying at 150 kilometers per hour, right? This is sort of what gamma rays are. They're incredibly. So far, it's very hard to observe gamma rays. And so far, the only thing that we know can actually generate them is our supermassive black holes or merging of a normal black holes. You don't really get them in planet formation or in star formation because there's nothing energetic enough to actually create them there. You need incredibly high temperatures of like millions and millions of Kelvin or degrees.
I did not know that.
I was wondering, when the gamma rays come out of the black holes, what do you think?
Hello.
Oh, just a second.
Forming new planets and stars.
Hi.
I'm sorry, ask your question again. Zarik Alvik, just wait a second. We're just finishing with the one guest. Could you repeat your question again?
I knew that gamma rays come from black holes, but I was wondering, what do we know about them forming new planets and new stars?
So gamma rays can't really create...
Or do we know anything about that?
Gamma rays can't really create stars. They are so incredibly energetic that they mostly just pass through all the gas that would eventually form stars or form planets. They might heat it up a little bit and hinder it a little bit, but it's a very tiny amount. You need something that doesn't just fly through, but actually sort of deposit their energy, like other gas moving at slightly smaller speed. So, yeah.
All right. Thanks for your question. Hopefully that helped a bit. All right. Who's next, Chris?
The next person is Liz.
Okay, Liz. Hello.
Good evening or good morning, depending on where you guys are. I just had a question about kind of generally what you were talking about, Dr. Scholtz. I'm coming from a complete place of ignorance. My brain does not quite work this way, but I'm just curious. You've been throwing out, these numbers, whatever's 300 billion years ago and 70 billion years ago. How can we possibly gauge time in that magnitude? Like, how do you, I know like carbon dating, but I don't think,
So it's actually one thing that we, as scientists, very quickly forget about. So when it comes to measuring how old the universe is, that actually comes from, we look at the way the light shifts from its normal wavelength of its normal to sort of higher and higher wavelengths. So it's something called the redshift, right? And then we have very particular models about what's the content of the universe and how the universe is expanding, right? That's the Hubble Constant that you might have heard. And based on that, you sort of estimate like, okay, that was 13.7 billion years ago when the universe was created by the Big Bang. When it comes to the other one, is how do you actually gauge those numbers as a human? You kind of don't. I float things like numbers around of, I don't know, for example, that this is going to be the energy that I will receive from these observations, or the power actually, is going to be 10 to the minus 29 watts per meter squared. How can you imagine something 10 to the minus 29 the same way? How can you imagine that is something, 13.8 billion years when the lifespan of a human is 60, 70 years? You just kind of get used to it. It becomes kind of a number. You get this handle on it that you, for example, know that, it's going to take 100 million years to stop formation of stars in a galaxy. So you kind of create that as your benchmark, and then you kind of move one way or the other. But I guess it's like with any big numbers in any life, like, I don't know, huge sums of money. For example, how do you imagine $43 billion? Right? It's something that we would never have as a human. Thank you. We would never kind of imagine as humans, right? Like actually having. So from that perspective, it becomes just a number. But you create this, you rely on your knowledge to be able to swim in these numbers, if that makes sense.
Yes, thank you. I appreciate it. I hope that wasn't a dumb question.
No. It's something I have an existential crisis about every like, I would say 4 months. I'm like, what the hell?
You're not swimming anymore. You're drowning in them.
No, I would like to persuade myself that I'm actually swimming and not drowning, but, don't make it too hard on me, Jason.
Okay, I'm sorry. I was just trying to make an analogy of the opposite of swimming. I'm sorry. So you're doing some doggy paddle from time to time in the numbers. How's that?
Yeah, definitely.
There we go. Thanks, Liz. Appreciate the question. It is hard to wrap your head around giant numbers like that, but when you're in a specialized field, everything just becomes normal to you. And it's very alien to people who are outside your field. Who's our next question going to, Chris?
Okay, so yes, we have Paula, then Indra, and then Zirak, and then I'm going to bring up Mario.
Okay, perfect.
Hi, Dr. Scholtz. Nice to have you tonight. This is fascinating, and I'm kind of like Liz. I'm very knowledgeable about this, but I like the reference that what stays in a black hole, it's almost like the Las Vegas of the universe. But kind of goes with the midlife crisis of the universe. So my question is, do all black holes eventually take out the galaxy that they're in? And because you said it heats up the gases and they need cool gases, and do they increase in size and eventually take out that galaxy? Or is it something that just kind of waits on the sidelines, and develops? So that was kind of my question. My second question is, I'm sorry, Jason, but I have to ask what kind of pets you have, because I always am fascinated to hear.
We didn't get to that. I know. I'm sorry.
I know, and I'm sorry, and I don't mind to interrupt with that. But if you could answer that too, I'd be so grateful. So thanks.
Okay, so from top to bottom, no, the black hole in the center doesn't swallow. It so far we have seen that they capped in their mass like a few times, billion solar masses. The galaxies kind of grow in size around them as well, because they also use up the gas to create stars and to sort of become bigger. So that's why the relationship of 1 to 100 in sort of masses kind of stays relatively often, actually very often. It's a very tight correlation. Okay, not really exactly tight. For astronomy, it's a tight correlation. So it never swallows them. It never outgrows it. The galaxies are there to stay, to live. Also, right, what I said at the beginning is that once the star has sort of a stable orbit around the center of the black hole and around the center of the galaxy, right, our sun is never going to fall into the supermassive black hole in our galaxy. It's way too far away.
Thank goodness.
Maybe the collision with Andromeda Galaxy in 2-3 billion years is going to sort of upset things a little bit, and we might migrate into the center of a galaxy. But honestly, I don't it's going to be a mess. Who knows? Probably not.
That's a problem for future us, Dr. Scholtz.
That's a problem for the future right after global warming. We need to sort out how we survive the collision.
Yeah, we got other issues.
Yeah. Sorry about being so dark. It's almost 2:00 in the morning. When you said, does it sort of kill the galaxy? Well, we think it sort of kills the star formation or the formation of new stars. We think so. Because it heats up the gas or it removes the gas from the galaxy, it probably stops forming. And you might have heard that there are sort of blue disky or blue spiral galaxies. Mm-hmm. And then we have something that's called red elliptical galaxies, sometimes referred in astronomy as a red and dead galaxy. And that's because they no longer form stars. And it's, again, this is highly debatable or highly debated in the community. What is the role of supermassive black holes of transforming spiral galaxies into these elliptical galaxies? So I think that there is this whole process, this whole phenomenon is called AGN feedback, and I think it has a profound effect. I think it's not like a rapid process that suddenly just kills all the formation of stars in a galaxy and just completely transforms it into the elliptical galaxies. I think it's something that happens over billions of years, but I think it's happening. I hope that answered that question. To the pet question.
Oh, yes, and your pet question.
To the pet question, I'm afraid I come from a household where pets was never really discussed or an option. I think mom wanted a dog, but never really. We always were like very much out of the house, so I think my dad thought it would be quite cruel towards the dog that we would leave it constantly at home. So we never had a dog or a pet at home. We would sometimes go and travel around Europe for like 3 weeks as well, so that would make it quite difficult. I had a best friend who had a golden retriever called Navax, who was an utter hilarious chump, and I loved visiting and walking him.
Aww.
And then my partner, she had a red Irish setter. That was just the most ridiculous dog ever. Not the smartest dog that was ever born. Completely stubborn, but absolute cutie. And they also have a cat. So when I visit my partner's my girlfriend's family, I get to see the Tabitha. I actually saw her 2 weeks ago. Very needy cat, but in a way that she doesn't want to show you that she's needy. She just sort of turns up, and if you pet her, she's going to be very happy, but she will never demand it with a straight face. But I think the dream is with my girlfriend to eventually get once we can get a house, is to get a golden retriever or a dog. I think we both miss a dog, having a dog.
Well, thank you very much. I really appreciate you taking the time. Thank you. It's a very fascinating subject. Thanks very much.
Is all the bad news about climate getting you down? Then you need to listen to the Climate 21 podcast, the weekly podcast dedicated to highlighting successful climate emission reduction stories. With over 77 episodes already published and a new one every Wednesday, there's always good climate news to hear. Check out the links to the Climate 21 podcast in the show notes, or search for Climate 21 in Apple, Spotify, or wherever you get your podcasts.
Great question, Paula. Is it Indra next, Chris?
Yeah, it's Indra, Zirak, and then Mario.
Yeah, Mario, we see your hand. We'll get to you, don't worry. And then it's very early in the morning for Dr. Scholtz, so we'll be wrapping up after those questions.
I think I'm up already, so if it takes another half an hour, 45 minutes, or 15 minutes, I don't think it's going to make much of a difference. So if people have questions, don't worry.
Okay, you're a trooper, sir. Over to Indra.
Okay. Thank you so much, Jason and Chris, for holding this space. And I have a question for Dr. Scholtz. I am so curious to know about what your thoughts are about the accuracy of black holes that are depicted in movies, and if there is a particular movie that you have noticed that does seem to be accurate. I mean, one I was just thinking of was Interstellar. That movie, right? And I'm just thinking, I'm a producer also, and I make movies, so I'm just curious. I've never been involved in any sort of science movie, but I love them. It's just a fascination, and so my mind just went straight there when I was hearing all the descriptions and you defining certain things, and I was just thinking, well, what we're seeing, is this just creativity, pure creativity, or is some of it based on science?
I love it.
I love films, but except for Interstellar, which was like the first thing when you said black holes, I can't think of any other film straight away. I think most of the time, I would say astronomy and astrophysics is a second thought when it comes to I think quite often they also try to make sort of black holes in general this evil menace, super powerful, and as I said at the beginning, right, gravity still applies here. So you can't, just because something is going to become a black hole suddenly doesn't become super strong that will rip everything apart. It will rip everything apart if it happens sort of to be close, but not necessarily, right? Like I said at the beginning with the sun, the analogy with the sun. Interstellar, I don't know if people know the story behind of how they actually modeled the physics, because they put things, they actually asked a couple of black hole accretion scientists to put in not only Newtonian gravity, but also general relativity and all of these kind of things in order to model the accretion disk, and in order to get the special effects and the CGI as accurately as possible. And they actually managed to get 2 or 3 science papers out of it.
Oh my goodness.
As much as I don't like Interstellar as a film. I did not enjoy it. I think I was like, oh, we solved time paradox, but I think they just still have it. Anyway, I can go on a rant in there. But
that's interesting that you say that you didn't like it because of the way that's what I'm curious about too. I love to hear this.
So I actually think that in terms of the physics was amazing. I mean, they actually got the accretion. We have seen something similar, 5-6 years later, when we imaged the supermassive black hole for the first time, where you actually can see the light from the opposite side of the supermassive black hole, because the gravity right at the close of the event horizon, the bending of the space-time is actually it actually bends the light rays. So that's why you see the other side of the accretion disk. They did it incredibly. And as I said, they got multiple science papers out of it.
So the time slows around a black hole. Is that true? Like, did they get the time thing?
That is also true.
Okay.
That is also true. What I would say is the one thing that they had to take some creativity. And this is where I am not an expert in sort of small scales around supermassive black holes, and especially sort of these lower mass black holes, like the Gargantua or whatever it was called in the film.
Yeah.
I don't think you can create planets around it. Or I think it would be incredibly hard to create planets around it, especially with atmospheres. For several reasons. Number one, you would essentially either it was a star that had a solar system around it, and then the star exploded in a supernovae, creating the black hole in the middle. And then I would say, well, the supernovae would wipe out the planets, so you can't have the planets around the black hole if it's a stellar remnant. And then I'm saying, well, how else can you actually? I don't think you can actually form stars in an accretion disk of a black hole like later on, because accretion disk will have a temperature of 5 to 50,000 Kelvin. You cannot create a star, coalesce anything at such a high temperature. So from that perspective, I don't think that part was scientifically accurate. Was it necessary to get the film the right way and have the time dilation around the supermassive black hole? Yeah, sure. And that was really exciting.
You couldn't have evil Matt Damon if there was no planet, Dr. Scholtz.
Yeah, exactly. It was a necessary thing to do. Yeah, it was a necessary thing to do. So I'm kind of split where they managed to get actual science papers out of it because they did amazing simulations.
Oh, that's cool.
And then there were a couple of things where I'm like, oh, come on, yeah. I would say one last comment to that question. If you give me a film and you say, yeah, we were just sort of making fun of, it was a science concept, we took it, and that's fine. Star Wars, Star Trek, I will never judge it for its accuracy in, the Newtonian physics of space battles completely doesn't make sense in that one. That's not how starfighters would work. I would be like, I don't care. It's Star Wars. It's cool. Right? Jedi and lightsabers and Sith, that's amazing. However, if you're going to give me a film where...
I love it. Okay, here we go.
If you're going to give me a film, just one last thing. If you're going to give me a film where you're going to say, oh, it's perfectly scientifically accurate, we have told all of these scientists, and it's amazing. And then I'm going to pay attention to the physics. And if I spot mistakes, then I'm like, well, you still didn't do it properly, guys. You just kind of told everybody that you did it, but you just cheated on your homework, or you ignored the advice of the scientists. So why did you have them in the first place? So,
and I'm going to answer that last part is because writers and producers take liberties. That's why. But I was so curious on your thoughts, and I loved the constructive feedback on it. It was very entertaining. Thank you so much.
Thank you for the question.
Great question. So Indra, if you're ever producing a movie about science and you for some reason need some plot hole that the actual plot hole is a black hole, you now have somebody you can call.
Oh, that's right. I know. I'm going to call.
And I'm most likely going to answer, well, we don't know. It's really tough to find out.
So you can do whatever you want. There, that's the answer. Okay, over to Zirak, right, Chris? And then to Mario. Thanks for waiting. Thanks for waiting, people.
Hello, everyone.
Hello.
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 I hope everyone is having a good time, and thanks for giving me this opportunity. I'm from computer science background, so I might sound newbie, but I wish I could go back in time and be a guy like Sir Scholtz. So basically, I have two questions. Why every object is round in this universe, like stars and planets, except asteroids and the smaller bodies, I can say. And my second question is, can you please tell us more about wormholes? Like, does they lead us to multiple universes? Like, does multiverse even exist, like we have seen in multiple movies? And that's it. And the last, Mr. Host, I love your talks.
Oh, thanks
for taking my questions. Yeah,
and those are great questions. Thanks for being patient. Yeah. Well, Dr. Scholtz, Dr. Scholtz, you're up. Those are good questions.
Thank you. This is why I love doing outreach. You just keep getting surprised by these amazing questions. Like, all of these questions were amazing. Okay, why things are round. There is actually very I would say, simple explanation. If you have, let's say, 4 stars, gassy planets like Jupiter, Uranus, Neptune, or any sort of all these gassy ones, they are essentially supported. There are 2 forces in effect. One is gravity, because everything is sort of collapsing under its own gravity, even the sun. And the other one that's keeping it away is the pressure from the fact that the gas has temperature, and which means that all the atoms are sort of moving around, bumping into each other, and that creates a sort of thermal pressure. We call it a thermal pressure. I think proper physicists and chemists might call it something different. But anyway, so you have all of these forces sort of balancing on each other, and since it's in a 3D space, you need something that's any single time it goes in one direction, suddenly the gravity or the forces are no longer in a perfect balance, and it basically pushes it back. If something suddenly becomes smaller, suddenly the thermal becomes too big, the thermal pressure becomes too big and expands it. So that's why you keep everything. So that's for gaseous things. For rocky things like rocky planets and why asteroids are not, that becomes purely based on it's actually material science question, and that is, again, you have the gravity.
Really sorry to, yeah.
You have the gravity, and the gravity is going to sort of push sort of everything right sort of towards the center, like on Earth. The thing is that as you increase the pressure on any rock or metal or anything, it becomes sort of putty-like. It becomes liquidy. If you reach some sort of a critical pressure inside the rock. And once that is done, basically it becomes sort of this putty or this liquidy thing. And once you have liquid, right, it can't hold sort of a shape, and it becomes a sphere, just like if it would be a gas. The reason why asteroids can have irregular shapes is because asteroids have asteroids are not big enough, so their gravitation, sort of the pressure from gravity inside them, is not big enough to make the rock plastic or like slightly liquidy, and therefore it can have like a weird shape. All right. So this is why once an asteroid is become too big, for example, you have Ceres or Ceres, which is a sort of a big asteroid / small protoplanet or small tiny planet, that actually became so big that suddenly it is spherical. One interesting thing, if you ever decide to go back to university and you do things about all of these things as a physicist, you will learn, your professor might give you a calculation, and that is what can be a highest mountain on Earth because of this sort of pressure of this like rock become plastic. And it turns out that for, I think, Earth, it's about 10 kilometers. I think Mount Everest can't go more than 10 kilometers. It will actually crumble under its own weight, essentially. Maybe it's slightly less than 10 kilometers. I think like Everest is becoming relatively close to its limit. But on Mars, which has much smaller gravity, right? It's a smaller planet. So there's less gravity there. And I think you can go up to 15 or 16 kilometers of the highest mountain, which is why their volcano is like very close to it. Again, it's actually pushing quite close. So yeah. So I hope that explains it. For the second bit, I am so unqualified to answer this question. And I think mostly because that if you want to do wormholes, you need to do a lot of general relativity, and you need to do a lot of actual proper science, or like proper physics and maths, which I have always tried to avoid it because it's way too hard.
Well, sir, can you? Sorry for interrupting, but can you please tell us, like, what does modern science have right now in terms of wormholes? Because I'm sure you can.
I think that currently we think it's like, oh, they are probably possible. They are theoretical predictions. Like most of these science fiction things comes from actual theoretical predictions, right? So I think they can be. I don't think we have ever detected one. I think we don't know how to detect one. We don't know how to create one. They have been kind of like, maybe you can have black holes. Wormholes where black holes are. Like, what happens to the material that forms into a black hole? We have no idea. What happens in a black hole stays in a black hole. We can't really create an experiment to test it. With parallel universes, I think that's basically, I would have exactly the same question. There are some theories that predict parallel universes. However, we currently, I'm an observational astronomer, right? I'm an experimental physicist, essentially. So I'm always looking at how can we create an experiment to prove this theory. And as of right now, there's absolutely no way of proving it. I think there is when you look at cosmic microwave background, when you pull up an image, if you just Google cosmic microwave background, you notice that there is this cold spot in one section, I think. And the cold spot is, I think it's few thousandths of a degree slightly colder than the rest of the CMB, rest of the background. And some people are like, oh, that's an imprint of another universe. Mm-hmm. Unfortunately, we can't prove it because we have only one universe. So we can't prove statistically whatever that cold spot is an actual imprint from another universe, or if it's a statistical fluke. You can't do a proof based on a sample of one, because you never know if we are living in a statistical fluke, or if we are, or if it's an actual signal that we can measure.
All right, sir. So I have a quick question. Can you please tell us about the singularity in the black hole? Like, where does it take us? Like, if we don't know about technically about wormhole, but what about the singularity in the black hole?
We don't know either. And I would say
Right.
in that case, we will never know, right? Because once any information passes, it can't escape. Photons, light can't escape. There's no way to communicate. So we just don't know. We can make
it is dropping information somewhere else, right? It might dropping information or all the things which it is capturing right now. It's just dropping it somewhere else in the multiple universes, or you can say other galaxies.
Other galaxies, no, because we would see that, right? We would see that suddenly there's the gas and everything just tossing out on somewhere else. We would spot that. My very naive question would be, if you are dumping it into a different universe, then black holes from different universes should be dumping things into our universe. We don't see that, so it's probably something different. But as I said, I think for that Jason needs to invite a cosmologist.
We'll have to get Dr. Katie Mack back again.
Thank you.
Yeah.
Thank you, sir.
That's such a great question. Thank you for speaking those really, really mind-bending questions to our expert. And Dr. Scholtz, thanks for trying to answer. Those are tough ones.
I'm honored, sir. Thank you so much.
Yeah, good job.
No problem. Thanks for the question.
Good job. Okay,
thank you, sir.
We're going to go to Mario now. Go ahead, Mario. You got your hand up and you've been waiting so patiently. Thank you.
Hey, sorry, I'm at work. I got one question in two parts. It's about indicating the mass of a black hole. To my understanding, scientists will measure the speed and orbit of stars going around the center of the galaxy. Also, you measure the amount of exhaust coming from Hawking radiation out of the center of a galaxy to indicate the mass of the black hole and power.
Are you a teacher who writes or a writer who teaches? If so, check out Chalk and Ink Podcast. We delve into the juicy intersection of teaching and writing. You'll come away with tips to boost your creativity and productivity. No matter what you're doing or where you're listening, you'll feel warm and cozy, as if you were discussing craft with close friends while savoring a cup of cocoa. Come join us. Click on the link in the show notes and check out Chalk and Ink today.
Okay, that's an excellent question of how do you measure the masses. I will answer the second bit. I don't think Hawking radiation has actually been detected. I think it's a theoretical radiation at this point. As far as I know. I think so. I will answer the second bit. No, we don't use the Hawking radiation. What we do instead, in order to measure the power of the supermassive black hole, is we just measure the light, the amount of light that's coming, and we measure it across X-ray, radio, UV, optical, near infrared, basically across the entire electromagnetic spectrum. We add it all together, and we will be like, okay, this is 10,000 billion luminosities of our sun, right? Actually, if that sounds really weird, that number, it's 10 to the, some of them are 10 to the 13, 10 to the 14 solar luminosities.
Yeah, I understand. That will give you an indication of its size as well.
Potentially. We are now getting into quite a complex accretion physics, for which I don't have. When it comes to the masses, we can do something different. So if it's something very much nearby, like for example Andromeda or our own galaxy, for example, our own galaxy, you might have heard results from instrument called Gravity on the VLT telescope that actually measures the orbits of the stars very close to our supermassive black hole. And there we can infer the mass of the supermassive black hole.
Yes, that's what I'm sorry.
Yeah, we can't do that at more distant galaxies. We can't actually see the individual stars around, right? Because we are way too far away. We can't detect individual stars. We just mostly detect, just the sort of stars in general. We don't resolve individual ones. So instead, what we do is we need to wait for them, or rather, we don't wait. We just look at it like, okay, is the black hole accreting? Is it feeding? And then as it forms the accretion disk sort of around the supermassive black hole. And then there are these clouds of gas, of hydrogen gas, sort of orbiting very, very close to the supermassive black hole. They are orbiting at roughly speeds of anywhere from 5 to 10,000 kilometers per second. And because we have observed these clouds somewhere in the nearby galaxies, we actually know how far away they tend to be from the supermassive black hole. And then we will just measure the speed. And then we use simple sort of Kepler's laws to estimate what is the mass of or Newtonian Kepler laws to figure it out. What is the mass of the sort of thing in the middle that's keeping them orbiting at such a high speed? It can be a little bit crude because at some point you can't see everything, so you start assuming things. You also start assuming that accretion disks and physics haven't changed for the past 10 billion years, which is a huge if. Usually, time evolution of the universe, like in the universe, is big if. But we get within factor of 2 roughly. We get the view, and we think we are reasonably close.
Now, at any point, now I understand. I understand that the accretion disk with the clouds help make it where you can't see directly into the center of galaxies, even our own galaxy. So you have different ways of measuring. That at any point does the Pythagorean method come into looking at the actual size of a black hole? Because I remember you were stating earlier, because I remember reading about how they'll use a satellite, not a satellite, but a radar satellite on the planet Earth, and as it orbits around, you can get 2 different points and then use the Pythagorean method and all that. Do you do that with measuring black holes? Does that come into play at any time?
Not necessarily. What you can do is you can, as I talk with the interferometry, you can link the telescopes across Earth and basically get huge radio telescope, and then you start mapping. If you Google M81 supermassive black hole event horizon telescope, you will get the image. It's actually a very famous, beautiful image. But from that one, I think this was the first time we could actually sort of directly measure the size of the event horizon. We could actually see the event horizon for the first time, and we could see it for the first time. Otherwise, you always kind of you never do it. It's it's very, very hard. Because we are too far away, essentially. Currently there is a limit to what we can see.
Thank you very much for your time. I'm going to step down to listener. Thank you for holding this space. I hope you hold more spaces like this, because I don't see a lot of science spaces where great scientists like this. I would love to see more of it. God bless everybody. Thank you.
Thanks, Mario.
Thank you.
We have Science Chat. We have Science Chat every Tuesday. It's a 1 hour earlier to help out our guest in the United Kingdom. How you doing, Dr. Scholtz? Do you have time for one more question?
I definitely have time for one more question.
All right. I hope I don't say this name wrong. Let me just get a little... Billy Jeet. Billy Jeet. Go ahead.
Bill Jeet.
Bill Jeet. Thank you, Chris.
Thank you very much, host and speakers here on the platform. Yeah, so I have studied, the gravity and the light years, and all the earthly mechanisms at all, right? So I was watching a documentary yesterday on Jupiter, right? It's a very big planet, maybe like 20 or 5 Earths by the radius, right? How is that Elon Musk capable to vision humanity to go to Mars, right? Because look at the moon, right? The moon is very harsh surface, and look at how Jeff Bezos' company is trying the trips to suborbital surface, and people come with an awe that, oh my God, Earth is the most beautiful planet out there. How the fuck Elon Musk is gonna convince people to go to all of these harsh climates? Not even climate, there is no climate. All of this vacuum of the space, right? It's the challenge, and I don't want my kids to be just blatantly following a hypno kind of fade, or like fake thing, right? Are we really made for the stars? And is our generation ready for the stars expansion? That's my question.
Well, can you answer that, or is that kind of outside your area of expertise, Dr. Scholtz?
That's a very much outside my expertise, but I might give it a stab.
Okay.
So yeah, I have done one course in formation of planets and exoplanets. 10 years ago. So this is going to sound from very much in ignorance, and most of the information I have is the same what is in the sort of what you get in the newspaper and the media. But don't worry.
Yeah.
I don't know. I kind of like the whole thing, exploring thing. When you look at the most science fiction books, terraforming planets takes thousands of years. This is not going to be any different. I think there are people on one side who say, oh, we need to sort of become a multiplanetary species. And then there are people who say, oh, all this money has to be sort of spent on Earth problems. I don't think I'm sort of sitting on the fence, but I think the question is actually, or the answer is a little bit more subtle. In order to really push science boundaries and learning, we need to explore space. We need to explore planets. We need to sort of send more robots and and everything on other planets, like Curiosity and other ones, and Voyagers. What I would also say is that the sort of Musk single-mindedness that we need to become like a living on multiple planets, I think we are about 100, 200 years too early. Great. Visiting other planets is one thing, and the amount of technology that we can sort of research while trying to achieve the goal, right? Look at how much technologies we have discovered by going to the moon during the space race. It was incredible, and we are benefiting it ever since. So we need to do this sort of research. I, on the other hand, don't think it's absolutely essential to become a multiplanetary species. Like you said, it's incredibly harsh environments on Mars. Whatever colony is going to be there will be sort of dependent one way or the other on the Earth. It's maybe they will get hopefully oxygen, water, and food sufficient, but in terms of any sort of manufacturing, any sort of industries, they will be heavily relying on resupply, and that is actually not what a colony should be. Colony should at some point become sort of self-sufficient on one level and start bringing something. So unless they start mining things or something like that, then what is the benefit of it? So I hope so. I don't think that is as scientific opinion, I think that's my own personal opinion as a citizen. I don't have any extra knowledge on the whole that would like inform my opinion to be better than any other person's on this chat.
Well, since we were speaking of space movies, good Matt Damon survived for a bit on Mars.
Oh, it's the best thing ever. I love the book, and I love Andy Weir's other books.
Yeah.
I'm actually staring right now into my library where they are.
I know. I can't, if The Martian comes on and I catch a bit of it, I have to watch the whole movie. It's so terrible. But
yeah.
Did we answer your question? Did the doctor answer your question? At least from his own perspective rather than a scientific one.
Can I speak?
Yeah, well, quick follow-up, sure.
Yeah, okay. Yeah, very, very brief. And yeah, thank you, Dr. Schultz. Yeah, my question was not very, I expected you to answer in a non-scientific way, and you answered in a combination of that. Thank you so much. Very kind of you. As well, from, if you look from Elon Musk's perspective, right, this guy thinks from the resources and materials perspective, right? On the Earth, we are trying to make hydrogen as well a alternative energy resource. Let's say you can tap Jupiter. Can you imagine how much hydrogen we will get out of there? I think we will get hydrogen for at least millions of years of hydrogen will get out of there, right? So these planets hold the materials under their belt, and if we can at least be there as a robot species, I think we will defeat the limited planet theory that we can only live on Earth, we can only be limited by Earth resources. So Elon Musk thought process is about really the materials and expansion and their scalability, right? If you spend X dollar on gas today, you can bring back the whole SpaceX gigantic ship full of hydrogen out of the atmosphere, and then that becomes a new recharge for the whole industry. So that's my perspective. We have never explored raw materials outside of Earth, and that is, I think, a 10x, 100x, or maybe a 1000x opportunity lying out there.
So I would make a counterpoint, if Jason, if you don't mind.
No, go ahead.
Yeah, there's loads of stuff. Absolutely. I think if you want hydrogen, the best way to make hydrogen is to do electrolysis of water. We have loads of water in the oceans. For that, of course, we need energy, and solar and wind energy is significantly a cheaper way of producing rather than getting hydrogen from Jupiter. You have to realize how big the solar system is. The sun, the light from the surface of the sun takes 8 minutes to get to Earth. It takes, and I think, another hour to get to Jupiter. Solar system is huge. I agree of where we can do a very efficient way of is mining asteroids. I would highly, highly suggest that you go on NASA's I think it's the Jet Propulsion Lab website or NASA's website, where they talk about mining asteroids. They even did plugin for Kerbal Space Program, one of my favorite games.
I love Kerbal.
Kerbal is great. So from that, I would say, we can there mine loads of rare metals in some asteroids, sort of capturing asteroid, bringing it close to Earth, and then sort of mining at the orbit and bringing it down. I think that's way more economical. I am personally excited about that. I don't think we need to go anywhere to the other planets. So yeah, it would be great. I think I don't want to be so doomy at 2:30 at night. 2:30 at night, but I think we should first sort out a way of not destroying our environment. And I think Tesla has kickstarted a huge, what is it called? A huge boom into electric cars. Unfortunately, cars are not the only pollutant. Ships are a major pollutant, and we don't talk about ships. I think coal and the way we make electricity is huge. It would be great to switch to nuclear energies, for example, because they are. I am a huge.
We have a nuclear engineer in 3 weeks on Science Chat, so we're going to talk all kinds of nuclear.
I am going to wake up at 1.
Yeah, you're going to wake up for that? Okay.
Yeah, I'm going to wake up for that. That sounds exciting.
Okay.
But I think this is a type of debate where we can literally be here for the next 5 hours.
I think so.
Both of us would make very good arguments one way or the other. So, yeah.
Awesome. Well, thanks for your question. We brought things close to home, and for most of the chat, we were talking about things that are very, very far away and not necessarily really impactful to your day-to-day life, but super fascinating. I think we'll stop the questions here and we'll let you go, Dr. Scholtz, and wrap up. Both Chris and I still haven't had supper yet, so we got home from a day teaching and set up the space. Thank you so much.
Thank you so much for moving it 1 hour early. I really appreciate it.
Yeah. And we just had our first guest request on Wisdom. I'm sorry, Wisdom guest. I'll give you a shout out. It's Andre. Thank you, Andre, for requesting. But we're just going to wrap up the chat tonight. And yeah,
I mean, we can do one more if Andre has a very quick question. Maybe we can do.
Okay. So
or up to you.
We'll try one more from Andre on Wisdom. So we're bringing Andre in. I just want to see if this works from Wisdom to Twitter Spaces here. Hi, Andre. Do you have a quick question for Dr. Scholtz about black holes or the galaxy?
Well, I came in right at the end of the discussion, so he's probably answered them all. I guess I just listened to the recording if there is one. And thank you very much. I'm really glad I stumbled upon your program. Yeah, I've heard about these galaxies that were discovered that have no black holes, no dark matter, and that they come from computer modeling that has shown that they could have been formed by being close to bigger galaxies that rob them of their black matter. Do you agree with that theory?
Dr. Scholtz, did you hear the question from Wisdom?
Yes, I have.
Okay.
And also, yeah, that's a very interesting question. Unfortunately, I have heard, I have seen the papers on Archive, which is the website where people put up astronomy papers. I am aware of it. So yeah, also theoretically, you can have a galaxy on galaxy interaction or sort of a merger during which you basically eject part of some amount of stars, some subsection of stars, away from what we call dark matter halo. It's where the dark matter is, and then it's not going to have a black hole, and it's not going to have any dark matter, and then it's just going to float as sort of this sort of bunch of stars. You can do that. Unfortunately, I can't tell you more about what is the feasibility. I would say purely from like first look, yeah, it can happen. I'm not sure how much I would call them a galaxy at that point. I think we are then like, what do you categorize them? They are not a globular cluster. They might be globular clusters, right? Those are just cluster of stars that I don't think have any dark matter. I'm 100% sure. I can always confuse whether they have loads of dark matter or no dark matter. I don't think they have any dark matter. And they, of course, they don't have a supermassive black hole in the middle. So they can be those. Yeah, that can. I think there would be quite rare things, and from perspective of galaxy evolution, that would be essentially just flukes. However, flukes are really interesting sometimes. So yeah, let's see in a couple of years what the models, whatever there are some people. I'm sure that there is a cluster, like a server running somewhere a simulation currently investigating what would happen. I'm sure of that. There are simulations running all the time. So maybe in 3 years, when they write it up as a paper, we might know more. Unfortunately, until then, I can only tell you it's feasible and it would be kind of cool, but probably not a huge impact on overall life of galaxies.
Thanks for your question, Andre. Appreciate it. Thanks for joining in. Thanks for joining in on Wisdom. It's very cool.
Thanks. I really like that. And I wanted to know what you're expecting from the new telescope, space telescope that's coming online. Is that going to shed new light on black holes too?
James Webb?
Yes, James Webb. My boss is one of the sort of chief scientists on the project.
What?
So I am hoping that I will get into the team. I know that they have a huge team already, so we need to figure out how I fit into the team, if I can bring, because there are loads of people who already have expertise in what I do. So we kind of need to figure out so they are not duplicates of people. We will be able to do galactic winds. We will be able to study the supermassive black hole seeds, from 13.4 billion years ago. One of the first supermassive black holes. We will be able to just, it's going to, on some level, it's going to revolutionize every part of galaxy evolution. On one hand, the fact that it's coming 11 years later, I think we have done so much more. The instruments on the ground-based telescopes have improved so much that it's not going to be. There's going to be some areas where the impact is going to be slightly smaller, but still there is going to be impact. But this is the whole thing when you bring a new telescope or instrument online. Until you look, you have no idea what you are going to see. So I can't tell you a prediction. Oh, we are going to see this, because we don't know what's there. We think we have ideas. But that's about it.
That's awesome. On Wisdom, you have a time. So Andre's time is up as a speaker. So hopefully you got your question there answered, Andre. So let's do a proper goodbye. I was just kind of shocked and I derailed us there, Dr. Scholtz. I'm sorry.
No problem.
Thank you so much for staying up so late to talk to us in North America and maybe Australia. But you're in Europe right now, and that time really is a problem. And for us running spaces, and you're such a trooper. So thank you for agreeing to talk to us about your area of knowledge.
Thank you very much for having me again. This was great fun. And thank you for all the amazing questions. It made me think hard, which is why I love outreach. I always kind of reflect on what I do and what I can improve. So thank you so much.
If you're on Twitter, make sure you give Dr. Scholtz a follow, right? Give him a follow right now, because as we go, as the space closes, you may forget who this person was. And it might be hard to find Dr. Scholtz on Twitter. So make sure you give Dr. Scholtz a follow. Doc, do you have time? There's 2 or 3 people who have DM'd me questions. Can I forward them to you? Would you have time over the next week to answer those questions? Or are you pretty busy?
I think I should be able to do it. I have a train journey on Thursday.
Okay.
I can squeeze it in.
Okay, so no
problem.
Yeah, no promises, folks. But I'll send your questions to the doctor, and if he's got time, he'll get back to you. All right, so we'll just wrap up, and I'll tell you guys what's happening next week. So thank you so much for joining us today for Science Chat. It's our first simulcast to Twitter Spaces and to the Wisdom audio app. It's awesome. Today's show is sponsored by the Bunsen and Beaker newsletter. It's in the nest on Twitter. So if you're not signed up for a newsletter, please make sure that you sign up. Special thanks to our guest tonight, Dr. Jan Scholtz. Such an amazing discussion. Whenever we talk about space, I sometimes got to sit and reflect on my life. And I'm going to be reflecting because space is so big and we're just so little. Pet Chat is back. We do a wholesome chat on Saturday at 6 p.m. Mountain Time, and that is also going to be simulcast to Wisdom. So if you want to come listen about the weird stories about Bunsen and Beaker for the week, come talk to us, and we'll open up the floor to people share their own pet stories. Next week in Science Chat, we have Dr. Holland, who is a bovine scientist that specializes in cows and sheep and goats. So it's going to be a pretty bad talk. No, it's going to be an amazing talk. And we can't wait to talk to Dr. Holland about her favorite cow. She has a favorite cow that she loves so much. So please join us then next week, Tuesday, with the regular time, 7 p.m. Mountain Time for Science Chat. Thank you so much for the people who asked questions. You guys rocked. And to our listeners, we had a huge crew tonight. It's awesome. I don't know if you saw, Tumblr was in the chat. Dr. Scholtz, the official account for Tumblr, was listening to you talk tonight.
I know, I saw. That's really cool.
I know. They've got 2.1 million followers on Twitter. All right. Thanks, Chris, for being my co-host tonight. I appreciate you. Thanks, everybody.
I appreciate you. I appreciate you, Dr. Scholtz, and all of his knowledge that was shared tonight.
Yeah, it rocks.
I think that's awesome. It's great.
Okay, take care, everybody.
Thank you so much.
Hope to see you Saturday for Pet Chat. For science, empathy, and cuteness.